Hello and welcome to this short overview of logistic regression. Before you watch this, you may want to watch my other video on odds ratios if you haven't already. So here we have two variables, x and y. X is a continuous variable, say it's the result of some blood test, and y is a binary outcome. Let's say it's the presence of some abnormality or the observation of some disease. If we model this with a simple linear regression, we're going to get this blue regression line. It isn't going to meet several of our regression assumptions, and the predictions are probably not going to be all that useful. The solution is to model the log odds of observing y instead in a logistic regression. From the fitted values in this model, we can calculate the probability of y given x. The predicted probabilities calculated from those fitted values are represented by these blue points along the prediction line here. So in this example, we are highly confident that individuals with a test value of x less than -1 are not going to have the disease. And we are equally confident that individuals with a test value of x greater than 1 are going to have the disease. So very high probability up here where x is greater than 1, very low probability of disease down here where x is less than 1. So how is this done? We'll use a generalized linear regression model, or a GLM, with a logit link function. That is, we'll model the log odds of y given x as a function of x over here. Now in the context of this model, beta 1 is the log odds ratio comparing disease risk in individuals exposed to x1 to disease risk individuals not exposed to x1. So this value, this coefficient, is the log odds ratio of y given of disease y given exposure to x1. That should be x1 there. Now there's some caveats that we should discuss here. So for one thing, beta 0 doesn't have any real-world interpretation for case control studies. For cohort studies, it does. So this can be interpreted as the log odds for the reference group. That is, when x1, x2, etc. are all equal to 0. But that's only true for cohort studies. Also, the odds ratio will always overestimate the relative risk ratio. Although for rare diseases, it's a pretty good estimate. So let's go off on a slight tangent to discuss odds ratios versus relative risk ratios. If we're given the total number of cases and controls in a study, so A is the total number of cases, and B is the total number of controls, then the odds are defined as the probability of y given x divided by the probability of not y given x. So this is the odds here. Disease given x divided by no disease given x. We can go through, a plus b cancels out, and we get a divided by b. The relative risk, on the other hand, is defined as the probability of y given x, which simplifies to a divided by a plus b. So this highlights one of the major advantages of modeling the odds. You don't need to know the prevalence or incidence in the population that you're studying. The sum of a and b here implicitly assumes that your counts are representative of the population under study. but we don't have to make that assumption for the odds. And this is why we often use odds ratios in case control studies instead of relative risk ratios. Not often. We always use odds ratios instead of relative risk ratios in case control studies. So the odds will always overestimate the relative risk because the denominator of the relative risk will always be bigger. We have the denominator here is b, the denominator here is a plus b. So this is always going to be a smaller denominator, meaning the odds will be greater. However, this bias is going to be negligible when the number of individuals with disease is small compared to the number of individuals without disease. So how rare does the disease need to be in order for the odds to be a good measure of the relative risk? That's the question. If A is very small and B is very large, then that denominator is going to be very similar to that denominator. And while the odds will be slightly higher, it's not going to be very different. So as it turns out, the difference in relative risk and odds is less than 0.01 up until the relative risk gets to, the relative risk gets to be about 10%. So a good rule of thumb is that as long as the probability of disease remains below 10%, the odds ratio is going to be a very good surrogate for the relative risk ratio. As you can see, after 10%, it rises fairly rapidly. Now, if you're studying a disease that is prevalent in the population, then you want to use a cohort study design and model the relative risk so that you can implicitly capture the disease risk in the population. You can do this using a generalized linear model with a log-link function, but these models tend to be less well behaved than logistic regression. We'll come back to that at the end briefly, but it can be done. So now that we're finished with that tangent, let's go ahead and look at the GBSG data set. Specifically, what is the change in risk of recurrence of breast cancer within a fixed time period given the grade of the tumor removed? Grade here is a number between 1 and 3. So let's pick this R output a little bit. If you are not familiar with the data set, by the way, I'll provide links to the Vanderbilt website where you can download it, as well as my tidied data set on GitHub. So go ahead and look down below in the comments for those links if you would like them. Here we have the R code that was used to generate this model, right up here. This is our call to GLM. And we see that D, which is the variable for disease in this case, which is our indicator of relapse, is modeled as a function of tumor grade. D tilde tumor grade. And we use as.factor to treat this as a categorical variable. And the family equals binomial argument tells GLM to do a logistic regression. And we're analyzing the GBSG dataset. So the other interesting part of this output for now is this coefficients section here. This is our model output. We have an intercept, which is the change so we have the intercept, and we have the change in log odds ratios for a tumor of grade 2 compared to individuals with a tumor of grade 1. And we have the log odds, the change in log odds for individuals with a tumor of grade 3, again, compared to individuals with a tumor of grade 1. We have standard errors of the estimates and associated test statistics and p-values, which all tell us that these estimates are significantly different from 0. And this model output is really the meat of what we want to discuss here. So how can we use this to derive some additional useful information, like something that you would put in a publication? You wouldn't put these log odds ratios in there. That wouldn't be what most people are used to looking at. So let's go ahead and calculate the odds ratios and their confidence intervals. We'll do that using the CI function from the gmodels package. When we put our model output through CI, that function, we are going to get some extra columns that aren't as important for this conversation. So we are only going to keep the estimate, CI lower, and CI upper columns. And we'll also remove the intercept, so we're just going to take rows 2 and 3 and not include the intercept in there because it's not really useful for what we're looking at right now. Also, we need to remember that these are log odds ratios we're working with, so we are going to pipe this through the exp function and exponentiate the results. So here are our results. The estimated increase of relapse in individuals with a grade 2 tumor is 2.9 times the risk for individuals with a grade 1 tumor. And that has a confidence interval of 1.7 to 5.1. Likewise, the estimated increase in risk of relapse in individuals with a grade 3 tumor is 3.4 times the risk for individuals with a grade 1 tumor. And that has a confidence interval of 1.8 to 6.2. Now, what if we wanted to calculate an odds ratio comparing grade 2 and 3 tumors? We don't have a beta in our model equation to measure that. To do that, we can use the estimable function. But first, we need to figure out what the contrast should be. So, if we want to compare the risk for individuals with grade 3 tumors, compare that with the risk of individuals with grade 2 tumors, we can subtract the log odds of the two. Okay, remember our disease is D, that's the variable we have in there. So we want to calculate the difference in log odds between grade 3 and grade equal to 2. This difference in odds on the log scale is the same as the ratio of odds when we exponentiate. So this result will be our desired odds ratio. So the log odds for grade 3 is 1 times beta naught, this is our intercept, plus 0 times beta 1, this is our coefficient for grade 2 tumors, this is grade 3 tumor, so that's going to be 0, plus 1 times beta 2, which is our coefficient for grade 3 tumors. So this first line is a grade 3 tumor, so we put 1 there. And then we're going to subtract the log odds for grade 2 tumors, 1 times beta naught, that's our intercept again, plus 1 times beta 1, that's our grade 2 coefficient, so we're going to put a 1 there, and then plus 0 times beta 2, which is our grade equal to 3 estimate, and so we'll put a 0 there because this is the log odds for an individual with a grade 2 tumor. We subtract that from this, we get 1 minus 1 is 0, 0 minus 1 is negative 1, and 1 minus 0 is 1. So these would be our contrasts, 0, negative 1, and 1. So we can put these into estimable, and the code runs off the page here, but the important parts are shown. This bit on the end is just, again, selecting the columns of the output that we want to display. We want the estimated odds ratio and the confidence interval bounds. So we give estimable our model and the contrast that we just calculated, and we tell it we want a 95% confidence interval. And also, don't forget, we need to exponentiate so that we get things that are not on the log scale. Now, when we look at the odds ratio, it looks like there's a slight increase of risk when you have a grade 3 tumor compared to individuals with a grade tumor, which is not surprising. But the difference is not statistically significant. We can tell that because the confidence interval crosses 1. So this is below 1, this is greater than 1. Now, if you remember our caveats, this is probably an overstatement of the risk of relapse because our outcome is relatively common in this case. And this is actually a cohort study, so we could model this using a log relative risk directly. We can model the log relative risk directly. So let's go ahead and take a look at that because I promised you we would. So the only difference in our call to GLM is that we change the link function to log. So the default is a link function. The default link function for binomial is logit. Otherwise, you'll see this code here looks pretty much the same as what we had above. The standard errors here are going to tend to be a little smaller than they probably should be, and we aren't going to go into adjusting for that here. But if we look at the estimates, they do look a little bit smaller than our log odds estimates if you go back and compare those. Because we aren't interested in confidence intervals, we're not, because these standard errors, again, are going to be a little smaller than they probably ought to be. So we're just going to look directly at the estimates and not calculate confidence intervals. And so because we're just looking at the estimates, we'll do all the calculations using the estimable function. In fact, we could have done this before. If we do want confidence intervals, we just have to put that confident equal 0.95 here as one of the arguments to the estimable function. Now we're going to tell estimable this time we want 3 different estimates. The first one is an estimate for beta 1. So that's going to be the relative risk ratio for comparing grade 2 tumors to grade 1 tumors. And here we're asking for beta 2, and that will be the relative risk ratio comparing grade 3 tumors to grade 1 tumors. And then again, we have the contrast that we just calculated, 0, -1, 1, to compare the relative risk ratio, or to calculate the relative risk ratio comparing grade 3 tumors to grade 2 tumors. So the relative risk relapse is about twice as high as large for individuals with grade 2 or 3 tumors. So that relative risk is about 2 for those when compared with grade 1 tumors. And there's very little difference, again, between the relative risk in individuals with grade 3 tumors compared to individuals with grade 2 tumors. This is even closer to 1 than the last estimate was. If the disease outcome had been rare, these estimates would have been much more similar to the odds ratios we calculated above. There are methods we can use to adjust the standard errors here, but we won't go into that right now. If you're familiar with the GBSG dataset, you may also know that we could do a survival analysis as well, since they include the time from tumor resection to relapse. But again, we'll save that conversation for another day. I hope you've enjoyed this and found it useful.